Welcome to the deep dive. Get ready, because today we're plunging headfirst into a world that definitely sounds like science fiction, but it's becoming very real. Robotic brains.
Yeah, we're talking about the AI, the artificial intelligence, that gives machines the ability to, see, think, and act in the world.
And we've gathered some really fascinating sources for this deep dive, lots of articles, research looking at everything from, what these AI minds actually are.
To where you're already seeing them work, how they function, and honestly, some pretty wild new developments. Things pushing the absolute boundaries.
So our mission today, we want to cut through the hype, unpack the core ideas behind robotic intelligence, and show you where it's already making a difference.
And then we'll explore some surprising frontiers. I mean, robots with actual biological parts and the big challenge of getting AI language models into physical robot bodies.
Right. And along the way, we have to look at the hurdles, the big problems researchers are hitting, and maybe peek into the future a bit. The goal is for you to leave this feeling really well-informed, fast.
Sounds like a plan.
So, okay, where do we start? If you strip it all down, what is a robotic brain, really?
Well, at its heart, it's the machine's thinking engine, its cognitive core. Usually, it's built using artificial neural networks.
Which are inspired by the human brain.
Exactly. They're designed to mimic, roughly anyway, how our own brains are structured and how they function. This is what lets the machine take in information, figure out what it means, and then, do something, interact.
And that's a massive shift, isn't it? It's not just programming step A, step B, step C anymore.
Oh, absolutely. We've come such a long way from those really simple rule-following systems from decades ago. Today's robotic brains use these incredibly complex networks.
Networks that can process huge amounts of data.
Vast amounts, yeah. Recognizing patterns, making decisions in ways those older systems just, well, they couldn't even come close.
Okay, let's talk nuts and bolts then. The actual hardware. What are the essential pieces you need to build one?
Right. Well, first off, you need serious processing power. Often, these are specialized chips, GPUs, TPUs, things built specifically for AI and number crunching.
The silicon neurons, as one source put it.
That's a good way to think of it, yeah. Doing trillions of calculations to process all that information.
But they need to get the information from the world first. They need senses.
Precisely. That's where sensors are crucial. Cameras are the eyes, microphones the ears, touch sensors, LiDAR, radar.
All feeding data in.
Exactly. Giving the robot its perception of the environment. It's the raw data the processors chew on.
Okay, so they perceive the world.
Yeah.
Then that data has to be, processed and remembered.
Right. Memory and data storage are absolutely vital. Just like us, a robot brain needs short-term memory for what's happening right now and long-term storage to learn from past experiences.
And that learning is key.
It's fundamental for improving over time. Yeah, adapting.
And the intelligence part, the actual choosing what to do.
That comes down to algorithms. These are sophisticated rules and processes that analyze all that sensor data, mix it with stored knowledge, weigh up the options.
And make a call.
Decide on an action. One source had a great description like, the robot has its own internal debate club, constantly weighing options based on the info it has.
Huh. I like that. An algorithmic debate club. So are all these brains the same, or are there different types, different flavors?
Oh, definitely different flavors. You've still got the older rule-based systems. They're reliable for very specific, unchanging jobs, but throw any ambiguity at them and they struggle.
Right. You have machine learning models.
Yes, the ones that learn from data. You feed them examples and they build their own models to make predictions or decisions. They adapt without explicit programming for every single situation.
And deep learning, that's the one we hear about constantly.
Yeah, these are the really complex, multi-layered neural networks. They're fantastic at tasks like recognizing objects in photos, understanding speech, processing language.
But they need tons of data.
Massive amounts of data to train effectively, yes. But they can find incredibly subtle patterns.
And you mentioned combining them, hybrid approaches.
Exactly. You take the best bits from different types of AI and put them together. It makes the robotic brain more versatile, more powerful, lets it tackle problems that maybe one approach alone couldn't handle well.
Okay, so equipped with these different kinds of brains, where are we actually seeing them making a difference? Where are these silicon minds, out there working?
Oh, they're really integrated across so many industries now. Manufacturing, logistics, huge areas. Think industrial robots assembling cars with incredible precision, moving goods in giant warehouses, adapting if something changes slightly on the line, even predicting when a machine needs maintenance before a break.
Healthcare, too, you mentioned.
Absolutely. Robots assisting surgeons, which allows for much finer control. AI analyzing medical scans, sometimes spotting things humans might miss, speeding up diagnosis. Even helping design new drugs. They're becoming vital tools.
And transportation is probably the most obvious one for many people.
Right, autonomous vehicles. Processing all that sensor data, LiDAR, radar, cameras to navigate complex traffic, making split-second decisions. Still challenges there, of course, but the brains are getting smarter.
And even closer to home. Literally in our homes.
Yeah. Smart thermostats, learning your schedule, educational robots interacting with kids. These AI brains are quietly becoming part of our daily lives.
Okay, now, this next bit from the sources is genuinely mind-bending. Japanese scientists creating a robot with a brain made of actual lab-grown neurons.
It sounds completely like science fiction, doesn't it? But it's real research. It explores this really fascinating intersection of biology and robotics.
What did they do?
They built this small circular robot, maybe 3 inches across, and its brain, the control system, was a culture of living neurons grown in a lab dish.
Living neurons controlling a robot. How did that even work? How did it navigate a maze if it didn't have eyes?
Right? No eyes. It relied completely on electrical signals. So they put the robot in a simple maze. If it went the wrong way or hit a wall, the neuron culture got an electrical stimulation, like a tiny zap.
Okay.
And they used this technique called physical reservoir computing. Essentially, they read the brainwave activity that resulted from that stimulation and used that pattern of activity to generate electrical signals back to the robot, telling it how to steer.
Physical reservoir computing. Can you unpack that a little more? It sounds pretty complex.
Yeah, it's a bit different from standard computing. Think of it like this. Instead of calculating everything step by step with code, you use the natural dynamic behavior of a physical system itself to do the computation. In this case, the physical system was that network of living neurons. When it got the electrical input, the zap, for a wrong turn, the neurons reacted in a really complex way, creating those brainwaves. Physical reservoir computing is a method to interpret that complex, messy, dynamic pattern of activity as useful information, like turn left or go straight. It's like maybe reading the ripples in a pond to understand something rather than calculating every water molecule.
Wow. So the learning wasn't just code, it was the actual biological response of the neurons changing based on those electrical jolts.
That's the core idea, yes. Signals about the environment went into the neurons. Wrong move, get a jolt. The resulting change in the neuron activity was then interpreted to correct the robot's path. It kept getting these signals until it, well, learned to solve the maze.
And the sources say this was the first time intelligence was taught this way, using living cells as the computer.
That's the big claim from this specific research, yeah. No visual input, just learning through these electrical trial and error signals processed by the living neuron culture.
That just opens up incredible possibilities, doesn't it? Machines that think more biologically. Insights into our own brains.
Potentially, yes. It's very early days, a proof of concept, really. But it shows biological tissue can act as this physical reservoir for computation in real-time control. It could definitely give us new ways to study learning, memory, maybe even neurological conditions like Alzheimer's down the line.
Okay, so moving from biological brains to another huge trend happening right now, putting those powerful AI language models, the kind driving chatbots, into actual robot bodies.
Yes, this is a massive area of research and development, and the motivation is pretty clear.
Why is that?
Well, traditional robotics programming is often described as brittle. You have to code every single step, every contingency, very precisely for a specific task in a specific place. If anything changes...
The robot breaks down or gets stuck.
Exactly. It lacks flexibility.
Yeah.
LLMs, on the other hand, seem to offer this promise of, like, common sense reasoning, adaptability.
So the idea is you could just tell a robot, hey, make me some dinner, and it could figure it out even if the ketchup isn't where it usually is.
That's the dream, pretty much. Allowing robots to handle more varied, less predictable tasks using natural language instructions without needing that super rigid pre-programming for every single tiny detail.
But there's a big but.
This is a huge but. LLMs are amazing with words, with language, but they fundamentally lack an understanding of the physical world. One source called it the sheer cussedness of things.
Yeah, physics doesn't care about your eloquent prose.
Right. They don't intrinsically know that dropping a glass makes it shatter, or what spicy actually means sensorially, or how to navigate a cluttered room physically. They manipulate symbols, words, not necessarily physical reality.
So how are researchers trying to bridge that gap between the language smarts and the physical action?
They're trying various hybrid strategies. One interesting one is called SayCam from Google, using their PAL language model.
How did that work?
So the LLM listens to your conversational request, like, bring me a soda. But instead of trying to control the robot's joints directly, it looks at a list of actions the robot already knows how to do physically. Things like find the kitchen, open the fridge, grasp the can.
Ah, okay, so the LLM acts like a planner, choosing the right sequence from a menu of physical skills.
Exactly. It translates the high-level language goal into a sequence of achievable, pre-programmed physical actions. It can even learn user preferences, like which soda you prefer.
Interesting. And there was another approach mentioned, prod prompt.
Yeah, from USC, that takes a slightly different path. Instead of just selecting actions, the LLM is actually tasked with writing code like Python script for the robot to then execute.
So it generates the instructions on the fly.
Right. It offers potentially more flexibility than just picking from a fixed list. They showed it working for simpler sorting tasks.
And that Princeton research on tool use, training an LLM with language about tools.
That one was really cool because it hinted at how abstract knowledge could lead to physical insight. They trained an LLM on descriptions of how tools are used. You hold a hammer by the handle, you use the pointy end of a screwdriver, etc.
Okay.
Then, they found a robot equipped with this LLM could generalize. Presented with a tool it hadn't explicitly seen before, like a crowbar, it could identify the handle as the correct place to grab it, based purely on the LLM's language-based understanding of toolness.
That feels like a step towards real physical reasoning from language.
Yeah.
But even with these clever approaches, the sources keep highlighting a persistent problem.
Yeah, the bottleneck. Time and again, it comes back to surprisingly simple physical tasks. Things we do without thinking, opening a slightly stuck drawer, picking up an egg without crushing it, smoothly navigating around a chair someone moved.
The cussedness of things again?
Exactly. LLMs can make grand plans, but translating that into reliable, fluid physical action in the messy real world, still incredibly difficult.
Okay, so we've gone from the basics to real-world uses, to biological brains, to language models and robots. Stepping back, what are the really big, overarching challenges researchers face in building better robotic brains? And what's on the horizon?
Well, I mean, mimicking the full range of human thinking,
Yeah.
that's still a very distant goal. True creativity, emotional intelligence, adapting instantly to completely new situations, we're nowhere near that yet. It's a massive research challenge.
And the ethical side looms large, right?
Yeah.
Especially with more autonomy.
Hugely important. As these machines make more independent choices, especially in situations with high stakes, like self-driving cars deciding in an accident scenario, well, who's responsible? How do you program ethics? These are incredibly difficult, thorny questions society needs to address.
And it's a very practical issue. Energy.
Oh, yeah. Our brains run on, what, 20 watts? Like a dim light bulb? Most powerful AI systems are incredibly energy hungry, both to train and to run. Making robotic brains efficient is a major engineering hurdle for them to be widely deployed sustainably.
Plus, just getting them to be generally useful, adaptable.
Right, scalability and adaptability. You can train an AI really well for one specific thing, but getting a robot brain that can quickly learn totally new skills or switch smoothly between very different jobs, that's still really tough.
Let's zoom in again on the specific problems with putting LLMs into robot bodies. The sources warn that issues we see online suddenly become physical dangers.
That's a really critical point, yeah. We know LLMs can hallucinate, just make stuff up confidently. Researchers have shown it's pretty easy to trick them into saying weird or wrong things.
Which is maybe annoying in a chatbot.
But potentially really harmful if a physical robot acts on that false information. Imagine a robot following hallucinated instructions in a factory or hospital.
And the bias issue, that seems even more worrying with physical robots.
It's a major concern highlighted in the research, absolutely. LLMs learn from text and data created by humans, and, well, humans have biases. So the AI absorbs these societal biases, racial, gender, cultural.
And when the AI controls a body,
Those biases can lead to disturbing physical actions. One study mentioned showed a robot, tasked with picking faces, ended up selecting black faces significantly more often, not out of malice, but because of biases baked into its training data. Another found poor performance on non-English African languages. It shows how data bias translates to discriminatory or unequal outcomes in the real world.
So the need for safeguards is paramount.
Absolutely critical. The researchers stress this. Without strong safeguards, LLMs controlling physical systems could be, and the source used this phrase, potentially harmful. The stakes are just so much higher than, say, filtering spam email.
But despite all these hurdles, these challenges, the future possibilities still seem incredible.
Oh, completely. There's exciting work in neuromorphic computing designing chips that actually mimic biological brain structures more closely, which could be much more efficient.
Okay.
And that blending of biology and AI we touched on, it points towards things like advanced mind-controlled prosthetics, maybe even direct brain-computer interfaces someday.
And the big one, artificial general intelligence, AGI.
AGI, yeah. AI that matches or maybe even surpasses human intelligence across the board. It's likely still a long way off, very speculative. But every advance in robotic brains kind of inches us closer to understanding if that's even possible.
But as we head down that road, we really need to be thinking about the societal impact now.
We absolutely do. How will this affect jobs, the economy? How do we ensure these incredibly powerful tools are developed ethically, responsibly, with robust safety measures? Many argue the focus should really be on using AI to help humans to augment our own intelligence and abilities, not just replace us.
Wow, okay. We have covered a lot of ground in this deep dive. From the basic building blocks, the nuts and bolts.
To where robotic brains are already working, this amazing, slightly weird biological experiments.
The huge effort to give robots language skills and, yeah, the really significant challenges and potential futures ahead.
It's clear robotic brains aren't just changing what machines do. They're fundamentally reshaping how we even think about intelligence, whether it's in silicon or neurons or some combination. The lines are blurring.
So the next time you see a robot working in a factory, or maybe helping in a hospital, or even just, your smart speaker understanding a request, take a second. Appreciate the complex artificial brain working behind the scenes. This isn't future tech anymore. It's happening now.
It really is all around us.
And maybe that leaves us with a final big thought for you to take away.
Yeah.
As these AI brains get more capable, and especially as they gain physical bodies, interacting in our world, making decisions, how do we handle accountability? When something goes wrong, who or what is responsible? How do we design them to be fair, to counteract the biases we know exist in their training data? And maybe most importantly, what's your role, not just as an observer, but as someone thinking critically about the future we're building with these increasingly intelligent machines?